So a little more about the engineering of how this all works. It's a series of steps, and we've got them all here. So you put the deuterium-tritium gas into this circular donut-shaped device called a tokamak. You then inject an electric current. The electric current, just like the electric current in a fluorescent bulb that you might see in lighting, it changes the gas, which we think of as the third state of matter, solid, liquid, gas, to the fourth state of matter, which is plasma. What does that mean? It means that the molecules separate and ionize. So the nucleus separates from the electrons. So everything inside there is charged, except, of course, neutrons that will be produced by fusion. So that's the first step. Then you continue heating with electromagnetic waves. And in fact, the electromagnetic waves are very much like the energy that you have in your home microwave, except more of them and, of course, thousands of times more powerful. The final heating system is what we call the neutral beam heating system. It's high energy neutral particles that can bombard the particles in the plasma. And so these three heating devices may or may not be used in the eventual design of the commercial fusion machines, but ITER allows us to test all three and to combine these techniques to reach 150 million degrees, 10 times hotter than the core of the sun, because in this magnetic fusion device, this is the temperature required for those particles to meet and collide. So clearly, at that extraordinary temperature, no material on Earth can withstand that temperature. So that is why we are creating this magnetic cage inside the steel cage of the vacuum vessel, precisely shaped like the steel cage of the vessel, but in a way that will contain and shape the plasma. So this magnetic cage is made up of three main magnet systems. The first one that you see, which is the central column, there is called the central solenoid. That device, and for scale, you can see the human at the very, very bottom. Do you see that? This human is standing there. So this is about 18 meters tall, if you include all of the structure, about 13 meters height of magnets made in 6 modules. The first one just shipped. I'll show you a photograph later. Just shipped from San Diego. That's being made in the US. Then we have these D-shaped magnets, which you see here in gold. The D-shaped magnets, those are being made about half in Japan, about half in Europe. And then you have round magnets. Since this is a cutaway, it's more difficult to see, but those are the dark red magnets, starting all the way at the bottom. One made in China, PF6. Then the next one is PF5, PF3, 4 and 3 here at this level, and then PF2, and at the very top, being made in St. Petersburg, PF1. So by the combination of these ring-shaped circular magnets, the D-shaped toroidal magnets, and the central solenoid, plus, we don't usually show these, but there are also smaller correction coils. So when I say small, the correction coils are on the order of about 10 tons, sometimes a little bit larger than that. Whereas these toroidal field and poloidal field magnets are ranging in several hundred tons apiece, and the central solenoid will be about 1,000 tons in total with its structures. So in combination, that is how we are making this precise magnetic field. Now, I want to talk about the size of ITER. I hinted at this earlier. Why would we build ITER at this size and not larger, not smaller? I said it was because of Q. But Q depends on 3 things, not just size. It depends on magnetic field strength, it depends on plasma density, and it depends on plasma volume. So the 3 tokamaks that you have here, first, all the way on the left there, you see Taurus Supra. Yes, so Taurus Supra is now called West. It's quite close to us, actually. This is a French tokamak. And then you see Jet. Jet is the largest tokamak that has been made so far. But if you look at these units at the bottom, normally I'm not including this much detail, but this is an important point. If you look at the units at the bottom, you see the volume of the jet plasma, see there, is 80 cubic meters, whereas the volume of the ITER plasma is a little bit more than 10 times more. That size is going to make a huge difference. How? Look at the heating that went into jet, 23 megawatts, and what did they get out? 16. That's still getting not a net energy across the plasma. You're still getting less energy out than energy in. A Q of 10 means that we're going to put 500, you see here, 500 megawatts of heating, for 50 megawatts of heating for 500 megawatts of fusion power to come from ITER. So that's why size matters. Now, if you increase the magnetic field strength, then you could also manipulate that ratio. And there are new magnets that I'll talk about later in the introduction. New magnets that are out that are also not yet scaled up, but it's possible that you would have stronger magnets which could influence the physical size of the device while still getting a higher output power. However, that would have other influences because, of course, if you contain all of this flux that we have, the neutrons that hit the walls, and you have it even more intensely, then your materials for your walls of the tokamak have to be even more capable of withstanding the neutron flux than those that we will use for ITER. One other thing that I did not mention earlier, we talked about differences in nuclear fission and nuclear fusion. For those of you who know nuclear fission and the fuel that goes in there, you have several hundred tons of fuel in there, uranium and plutonium, something very heavy. We talked about hydrogen being light, but here's the remarkable thing. In this gigantic machine, where the vacuum vessel has this enormous diameter, we're only going to put 2 to 3 grams of hydrogen, deuterium and tritium, in as fuel at any one time. So this is, again, something that says when you wonder how do we have all of this hundreds of millions of years of abundant fuel, that's why. Because fusion uses a tiny, tiny amount of fuel. So let's move on from the discussion of how ITER works and talk first about how we are building it. This next part will be about project management a bit. How is the project managed? And then we'll go on to look at some photographs of where we actually are today in June 2021. So I mentioned that all the members probably would have loved to have had the ITER site on their the ITER plant built on their land because there are obvious economic advantages. When the decision was made and the ITER agreement was designed, what members agreed on is that they would not simply send money to France or to Europe as the host member, but they would in fact provide in-kind contributions. What does that mean? Components, physical components, right? And that each of these 7 members would have a domestic agency to manage the companies in the industry that would supply these components. The central organization, ITER organization, manages here in Cadarache, and we manage the integration of all those components and the assembly. And of course, a key point, members are bound by the ITER agreement to share all of the intellectual property that is generated by the project. But this makes a very, very unique formula. You've got 7 ITER members, and because of Europe, really you're talking about 35 countries building one machine. And Europe, because it's the host, is responsible for 45%. All the rest, each of the non-European members are responsible for about 9% of these procurement packages. And what I've done here with this graph is to show you a relatively crude breakdown of how all that is. You'll see some of these components being built. But the question is that smart or is that awful? Was that a very smart way to build a machine? The answer is more subtle than you might think. Of course, it means that project management at ITER has to be incredibly, incredibly on tune. How you manage a schedule, how you integrate that schedule. All of these devices coming together have to have incredible precision. In other words, the machine that is built must be incredibly precise. Why? Because no matter how large you build a tokamak, the size of the particles, the magnetic particles that you are trying to contain, don't change. So the weave must be like the weave of your cotton or wool, the weave of a jacket or a shirt or something, a blanket. The weave must be ultra precise so that the neutrons are the only thing that escapes. It has to be able to hold in with the magnetic field all the other particles in order to be efficient. So doing that in a way that has all of these countries and their companies supplying this device and making it all fit together is what makes ITER probably the most complex human endeavor, engineering endeavor of all time. Is it good or is it bad? There are real advantages to doing it this way. And I hope that I can point some of those out as we go through the actual photographs. Now, this is just showing you a schedule. I'm not imagining that you're going to be able to follow all of this schedule, but what you'll see essentially is that where we are here in the middle of 2021 is at the point when a lot of the components are arriving. More will be arriving in 2022, 2023, and then we will be putting these things all together. The current schedule says that we are trying to have all the system commissioning done by the end of 2024 so that we can actually close the cryostat and have a year of integrated commissioning with first plasma at the end of 2025. Now, we know that there are challenges to that. We have managed to keep going during COVID-19, but we know that there are technical challenges. COVID-19 has slowed down our production rate, but it has not stopped by any means. And as we talk now, we're over 74%, nearing 75% of what we call total construction through first plasma. So that is every 2 months measuring about 25,000 different weighted activities all the way from design through commissioning that will help us to see where we are. So we have been making that steady progress despite COVID-19. Now, there's no float in the ITER schedule through first plasma. And so when you have delays, you have to try to find mitigation measures in some way, do some assembly in parallel, et cetera. But after 2025, you see here a 10-year staged approach. And the staged approach means that first plasma, if we make it in December 2025, would be when you really test the functionality of the overall machine. You don't have everything quite in there yet, and you're just running a plasma with hydrogen, not with deuterium tritium, and that allows you to make sure that you have a functional machine. After verifying that, you go back to an element of assembly where you add certain pieces. You go then into pre-fusion power operations, and you go through this series of stages with full fusion power envisioned in 2035. And so there is some float in this 10 years following the first plasma. So even if we do now reevaluate what is the post-COVID baseline schedule, and we have to make some adjustments to the slide I showed you earlier, we have every confidence that we will remain on this overall four-stage approach to fusion power operation.